Let me give you a brief overview of the techniques that we can use to find volumes of solids obtained by the revolution of a given region in the plane around a certain axis of rotation. There's basically two methods. One is the disk's washer, which involves computing the integral of the area of a disk. So in that case, if the radius is r, that's going to be pi r squared. Or a washer, which is if a inner radius is r and the outer radius is capital R, would be pi capital R squared minus pi little r squared, because I have the area of the big circle and I'm subtracting the area of the small circle. So it's not r minus r quantity squared. And then we have the method of cylindrical shells, which tells us that the volume is equal to the integral of the lateral surface of the shell. And if the radius is r and the height is h, then that's given by 2 pi r, that's the length of the circumference, times h. Because if you cut this and you unfold it, you're going to get rectangle whose base is the circumference, so 2 pi r, and whose height is h. Now the main question that everyone always has is, how do I know whether I should use this method versus this method? I'm going to tell you my suggestion is, first of all, you sketch a picture, and I'm going to illustrate it with this example. So we have a region bounded by the parabola y equals x squared, which is here, y equals 9, and x equals 0, which is the y-axis. So it's this region over here. You are either going to consider a vertical segments or horizontal segments. And then you're going to follow the rotation of one of those. The point is that if you want to consider vertical segments, let's do it this way. So like this. In order to reconstruct the whole picture, you would need to go like this. This means you're moving in x, and that's an integration in x. You need to see always one function on top of another one, so that you can recognize the length of this segment as the difference between two functions. Is this the case here? Yes. I always see the function y equals 9 on top of the function y equals x squared. So I know that the length of this would be 9 minus x squared for all this range. Now, depending on whether this rotates around a vertical axis or a horizontal axis, the rotation of this segment will produce a disk or a shell. Suppose that I'm rotating around a vertical axis, like this. Then the rotation of this will produce a shell. So I will need to use the shell method. Identify the radius, which for this case would just be x, the height, which is what we just said earlier, and then put it in the formula, and we would be done. On the other hand, if this was rotating around a horizontal axis, so let's suppose the x-axis in particular, then the rotation of this segment would produce a washer. So I would use this method. Computing the inner radius, which would be given by this function, so it would be x squared, and the outer radius, which would be given by this function, so it's y equals 9, and putting it in this formula. Now in this case, we use these vertical segments. If we used horizontal segments, would that have worked? Well, let's see. If I have horizontal segments, then I need to move from here to here, which means I'm moving in y, that's an integration in y. Do I always see one function to the left of another? Yes, I always see this one and this one. So they're gonna give me the length of this. I will just need to express this as x in terms of y. So this curve would now be x equals square root of y. And well, this one would be x equals 0, so the length of this would just be square root of y. And now if this rotates around the vertical axis, the rotation of this produces a disk. So I would put the radius in this formula, radius being square root of y. And if this was rotating around a horizontal axis, then this would produce a shell, and I would use this method. The radius would be here, r, the height of the shell would be this length, so it will be square root of y. So sometimes it's not going to be easy to solve for one variable, and that would preclude us to use a certain method. But the main point is that we need to see one function on top of each other always, or to the left of the other always. I'm going to illustrate that with one last example. Suppose we had, instead of y equals 9, suppose we had y equals minus x plus 1. So this picture, the line minus x is like this, it's shifted up 1, so this would be it, more or less. And this would be our region. Now, if I drew a horizontal segment, to reconstruct the whole picture, I would need to vary it like this. That's an integration in y. Would I always see one function to the left of another? No, because up to here, I see the line on top of this, so the length would just be given by the line. But then here, I'm not hitting the line anymore, I'm hitting the parabola, so now the height changes. So I still can use this method, but I would need to consider two integrations. One for this range, and one for this other range. So that's not the best thing we could do. Let's see. What would be the difference if I chose vertical segments? Then do I always see one function on top of another? Yes, because I always see the line that's on top of the parabola for all this range. So I can just do it in one integration. So that's what I was saying. That's the main point. That's how you should decide which of these methods to use. Just decide what's the direction of the segments that you're going to use, and then follow the rotation. So then, if this rotates around a vertical axis, it produces a shell, and you're going to use a shell. If this rotates around a horizontal axis, then it produces a washer, and you're going to use a washer. So it's not about, oh, which one should I use? It's about understand what the geometry of the planar region is, and if you have to slice it vertically or horizontally. Then just follow the rotation and you will realize what it happens. In this way, you don't need to memorize anything. You don't need to learn anything by heart, but you just understand what's going on.